We talked about in a previous video that the definition of the inverse of a matrix says something like, a matrix is invertible if there exists a matrix B such that, AB equals BA equals the identity matrix, which kind of alludes to this idea that there are potentially matrices that do not have an inverse. And so let's consider that in this video. So suppose we have this 2 by 2 matrix here, 1, 2, 2, 4. And let's go about using that sort of process we had talked about earlier for finding the inverse. So assuming it exists, the way we would find the inverse is by augmenting our matrix with the identity matrix, and then, row reduce. So we could do our row 2 minus 2 row 1, 1, 2, 1, 0. Okay, so 2 minus 2 is 0. 4 minus 4 is 0. And then 0 minus 2, this would be a negative 2. And this would be a 1. And what we see here actually is that, this bottom row would lead to inconsistent systems. Remember that kind of the reason we set this matrix up where we augment A with the identity is because we had this system where we had the variables A, B, C, and D, and we had these two systems we were kind of solving simultaneously. And so, we basically in this bottom row have two inconsistencies, 0 equals negative 2, 0 equals 1. So these systems would have no solutions. Okay, and so this would be a situation where there is no, so A does not have an inverse. And so we would say A is not invertible. Okay. And so if we cannot sort of row reduce A in order to get the identity to sort of follow through with this algorithm, then A is not going to be invertible. We'll see that more formally in a little bit, but I just wanted to start with this example. What does this mean for systems involving or equations, I should say, involving this matrix A? So a non-invertible matrix like that matrix A can lead to inconsistency. Let's consider this equation, AX equals B, where A is that matrix that we saw earlier is, not invertible, and try and solve AX equals B, where B is the vector 1, 3. If we try and solve this equation through just our standard row reduction, R2 minus 2R1, 1, 2, 1, 0, 0, 1. Okay, we could see this is inconsistent. So we have no solutions. Okay, and so one thing we'll see is that the equations AX equals B, if A is not invertible, if A is not invertible, then the system may be inconsistent. Let's consider another example. This time, instead of B being 1, 3, what if it was 1, 2? And we'll go ahead and try and solve this using our row reduction. So 1, 2, 2, 4, augment, row 2 minus 2, row 1. Okay, so 0, 0, and then 2 minus 2 is 0. So we actually have infinitely many solutions in this case where we have a free variable, right? We have a column without a pivot, and so we have a free variable. So if x equals x1, x2, then we might have x2 as our free variable, and x1 equals 1 minus 2x2. Same matrix A that is non-invertible, this time instead of no solutions, infinitely many solutions. So those two possibilities occur in these situations. However, if our matrix is invertible, this proposition will tell us that we do have solutions. So if A is an invertible matrix with inverse B, then any equation Ax equals B is consistent, and x equals B, big B, the matrix B, the inverse, times the right-hand side, the little b, the vector B, is a solution. In other words, the solution to Ax equals B is x equals A inverse B. And I'll point out here the term the solution. So we just have one solution in this case. So if A is invertible, if A is invertible, then Ax equals B has one solution, namely x equals A inverse B. So if A is not invertible, then we could have no solutions or infinitely many solutions. If A is invertible, we just have one solution. And remember, those are the only three options for these Ax equals B equations. We might have, one solution, infinitely many, or no solutions. So whether or not A is invertible kind of tells us, if we're in the one unique solution or, one of the other two scenarios. Just quickly looking at why it is true, if we had Ax equals B, multiply both sides on the left by A inverse, okay, and we end up with A inverse times A being the identity, so we end up with I times X equals A inverse B, so X equals A inverse B. So this is kind of a quick, not super formal, but a little bit of a proof about why that proposition is true. What about kind of this idea that we looked at earlier, where we have an algorithm of sorts for finding this inverse by row reducing the matrix A to the identity? Why do we know we can row reduce a matrix A to the identity if it is invertible? So suppose A is an invertible n by n matrix, then by that previous proposition, the equation Ax equals B is consistent for every vector B. Think about what that means when we actually row reduce A. That means that, when we row reduce A, just going back to some of the things that happen. So when it's not invertible, when we row reduced, we got, a column that did not have a pivot in either of these cases, right? We got that sort of row of zeros in the coefficient matrix in A. If it is invertible, then that has a solution. So, A must, the columns of A must span Rn, right? If Ax equals B has a solution, then we remember that, if A is V1, V2, down to Vn, if these are sort of the columns of A, right, then Ax is just x1 V1 plus down to xn Vn. And so if Ax equals B has a solution, that basically means that there's a linear combination of the vectors that make up the columns of A to get to any vector B in Rn. And so, any vector B can be written as a linear combination of the columns of A. Therefore, the columns of A span all of Rn, which means there must be a pivot position in every row of A. If we go back to some of those videos and some of the propositions we had seen about spanning, we would see that this had to be true. Since A is an n by n matrix, having a pivot in every row implies there is also a pivot in every column. So that is enough for us to know that we can reduce A to the identity. So proposition 315, the matrix A is invertible if and only if the reduced row echelon form of A is the identity matrix. So A is, a row equivalent to the identity. In addition, we can find the inverse by augmenting A by the identity and finding the reduced row echelon form. So in other words, sort of row reducing this A augmented with I to I augmented with whatever we have, that will end up being A inverse. So this is kind of our nice algorithm for finding the reducer echelon form of the matrix. And we'll see more examples of this in future videos.